So this is the most general linear restrictions hypothesis test, but it is actually the simplest, right? Let's think about, right? This is the form, right? The matrix R is Q by K with rank Q. Let's think about it. Like for example, if we learn, like if you make an assumption like this is one dimensional, like, or at the same time, your null hypothesis may include like beta 2 plus beta 3 equals to 0. Or you may include as much as you want, like this. So when you have multiple parameters involved and multiple equalities are involved, then you have to rewrite this as, I recommend you write this as this. Let's see. So r times beta equals a vector, right? This is q by k and k by q, k by 1, and this is q by 1. This is 1. Okay. So for example, when you have this kind of form, r is, the first one is about the first coefficient. And the second row is about 0 plus 1, 1, 0, 0. And the last is about this. And h vector will be h1, 0, 0. Okay? And then if you write r times beta 0, you will get as like beta 1, 0, beta 2, 0 plus beta 3, 0, and beta 4 minus beta 5. So if when you equate this to the vector, you get the same hypothesis as that. Okay. So this was just an illustration on an example. And then when you have that, say think about unrestricted estimator. The unrestricted estimator will be OLS, right? You are not imposing anything. You just have exogenous regressors, no restrictions on the parameters. So you have OLS. So I'm not going to go into detail. You are going to have OLS estimator. And then you know how it is distributed. You know it's asymptotic variance. So we are going to utilize that. Especially we know it converges to normal distribution V. V equals x transpose inverse expectation ui squared x transpose inverse not inverse here, excuse me, x transpose, okay, inverse here. So the standard formula is the OLS estimator's variance. Okay, then we have unrestricted estimator, and then let's think about our design of test statistic. We are going to calculate the unrestricted estimator, and then we are going to calculate the restrictions, and we will compare if it is close to, similar to the vector h or not, right? So I mean reject the null hypothesis if your restriction minus h is different from 0, right? Because our null hypothesis is all beta 0 equals h. So we are just replacing beta 0. This is unknown. R and h are known. So we replace this with the unrestricted estimator and calculate the distance, right? So this is about the distance. So difference from 0. So we need distance from 0. Distance of this guy from 0. That is our idea. And that means when you think about distance for a random variable, we are going to think about this. So when you have this converges to normal distribution 0 omega, let's say, then we know it's transpose omega inverse, and the transpose will converge to chi-square rank of omega. Okay, that is a simple theorem we can utilize. So then let's find omega, and then think about like a test statistic utilizing omega hat instead of omega. And then this much will be your test statistic. Let's first find omega. Like say, so let's start from the OLS and minus beta 0 converges to normal distribution 0 and V. So this is true even if the null hypothesis is wrong or correct, right? This is just OLS result, okay? But now let's think about, but we are in, and from here, we are going to multiply the restriction matrix. Then, obviously, it will go to this form, right? So then, as you may guess, this guy is going to be omega. I'm going to write that as omega. So let's write it as omega. Okay. Now let's think about what happens if H0 is wrong. Okay, first let's think about the wrong case. In this case, R times beta 0 is different from H. So I'm going to write it as H plus delta, right? So additional delta is the difference, how much the null hypothesis is incorrect. And then what you calculate, right? What you need is you are going to calculate this guy, right? So this is what we are calculating, what we are interested in. So these have to be written as minus R times beta 0 plus R beta 0 minus H. That is, this will converge to normal distribution, small p1, but the other guy is going to be square root n times delta. So no matter what omega is, so this guy transpose omega inverse times this guy. So what I'm saying, in this guy we have to bring it here and here. Then it is something like chi-square something plus it's squared, like n times delta transpose omega inverse delta. So this is always going to go to the infinity, positive infinity. So remember, like what I'm showing here is when the null hypothesis is wrong, right? When it is wrong, the distance will diverge. Now then, let's think about what happens if H0 is correct. And then square root n times R times beta hat n minus H, this is what we are going to calculate, equals R times beta hat un minus R times beta 0. Because remember, the null hypothesis is R times beta 0 equals H. Okay, so H is R times beta 0. And then this is exactly what I had. Okay, so the null distribution is already calculated. Now what remains here is you are going to calculate, we need to calculate the variance, omega hat. That is the only remaining thing, but that's also easy. Omega was defined as R times V times R transpose, and we will calculate V hat as the sample average of X transpose inverse and sample average of U hat I squared, residual squared X transpose, and then sample average of X transpose inverse. Okay, and here of course the residual will be defined as X transpose beta hat n. So as OLS, right? No difference from the OLS. And then given this variance, OLS variance matrix, your omega matrix will be R times V hat times R transpose, because R is known. You can calculate the matrix R, you know that. So omega hat can be calculated, and then the test statistic will be this guy. Okay, so rearranging that, n times R beta hat U n minus H transpose omega hat inverse times R beta hat U n minus H. That converges to chi-square Q because we assume that rank of R is Q, right? So rank of omega is rank of R times V times R transpose, but V is full rank in like under the full rank assumption. V is full rank, then the rank of this guy is Q. So we get the test status. You can calculate everything in here. Now then, how can you choose the critical value? When you have Q, chi-square Q distribution, you have to find a critical value such that left-hand side area is 1 minus alpha, and this area is alpha. So it is 1 minus alpha quantile from chi-square Q dimension. Okay, so